Hello, we are Group 39, part of the ZF Energy Reduction Team. My name is Jesus Davalos. I am the project manager.
I'm Ruben Rocha, the assistant project manager.
I'm Robert Ferry. I'm the electrical design lead.
My name's Austin Fortman. I'm the mechanical design lead. Let's take a look at our problem description. First, we have excessive energy consumption as our operations rely on continuous energy use regardless of actual demand. This leads directly to high operating costs, especially since heating, cooling, lighting, and fans run around the clock. On top of that, this inefficient use of energy contributes to a larger environmental impact, increasing our carbon footprint and greenhouse gas emissions. A big part of the problem lies in inefficient systems. Equipment is often being operated beyond what's necessary, wasting energy in the process. This overuse also causes increased wear and tear, shortening machinery lifespan and driving up maintenance costs. Clearly, there's a need for energy reduction. By optimizing our heating, cooling, and lighting systems, we can reduce costs, minimize environmental harm, and improve overall efficiency.
For our scope of work, we are focusing on the production building and the division building. In the production building, we're focusing on shutting down the boiler during periods of non-peak demand. And in the division building, we are focusing on lighting control optimization with motion sensors and timers to make the lighting more automatic and reduce any overuse of light.
Our team designed an energy reduction system focused on improving efficiency and cutting unnecessary energy use. One key component is the use of electrically actuated ball valves to divert steam. This helps minimize heat loss by only sending steam where and when it's needed, reducing waste before it returns to the boiler. Another feature we designed is automated indoor lighting controlled by motion sensors. This ensures that lights are only on when spaces are occupied, which significantly cuts down on energy consumption. While we won't be installing the system ourselves, we've equipped them with a fully developed design with projected ROI to support future implementation.
So for the cost savings breakdown for the steam heaters, which would be the production side, we were shooting for a annual savings of, or a monthly savings of 4.2%, which would initially break down to $3,705 for every peak month savings, which that would be a 5-month period of use for the boilers. That's just the minimum that we forecasted for the future. We do believe we can get more than that, potentially 8.3% savings, which would be a $7,400 5-month peak saving, and also a 12.5% savings for the 5 peak months, which would be 11,000. But just for the minimum 4.2% savings, we believe that would be $3,700 annually. And with our system cost being $4,400 for the initial investment and for our annual savings being the $3,700, it comes out to a 1.2 year payback period for the production side. For the lighting division building, this chart over here, you have the cost breakdown of how much it costs to run their lighting consumption per year. And at a 16-hour usage rate per day, 365 days a year, it comes out to about $8,800. And if we're able to reduce it by 2 hours, just having a 14-hour runtime per day with the motion sensors, that would bring down their cost of $7,700 per year with the annual savings of $1,100. with the motion sensors integrated into the building is a 85,000 square foot area of work. Our motion sensors that we've researched on have a radial coverage of 1,260 square feet. So approximately we would need about 50 motion sensors throughout the building, just because we wouldn't need a motion sensor in every single empty space in the building. Each motion sensor comes out to the price of about $80. So with that in mind, our total cost being about $3,900 and our annual savings of $1,100, we have a payback period of 3 years and 7 months, which is still within industry standard for a payback period. Thank you.